Okay, welcome back. Continuing on chapter 12. We are on, out of the book, we're on page 311, chapter 12. We just want to talk a little bit about the PowerPoint here. We just discussed iron powder can increase the deposition rate, can also increase the speed, and improves the weld appearance. And you'll notice that right away. A properly welded 7018 weld bead is a very nice looking weld appearance profile, to where you don't feel like you have to grind it down to have it look really nice. 6010 is going to be a little bit different, not quite as nice of a weld appearance, so forth. So let's talk about how iron powder converted to steel in intense heat and contributes metal to weld deposit. So again, it's iron powder, so small little flakes. And remember, the melting point of steel is roughly 2,800 degrees. And from previous chapters, we know now that the arc and the center of the weld puddle can get as high as up to 9,000 degrees in the center, 7,000 degrees on average. So we're melting those little iron powder flakes and contributing it into the weld pool. So that's how we're getting it in there, okay? We're above the melting point, letting it disperse. It improves the deposition rate, okay? As you're looking through welding material specs, you'll see a lot of times weld deposit, but you look at deposition rate. So the iron powders may have a 2-to-1 versus 60-10. They may have a twice as much deposition rate, being able to put down more material, okay? All right, low hydrogen electrodes improve welding of steels that tend to be porous and crack under the bead. We'll get more into the underbead or hydrogen cracking. So what happens, let's talk about it for a minute. What happens here is low hydrogen rods, they're less susceptible to bring hydrogen in and moisture into the rod. 7018 specifically needs to be, if it's to open atmosphere, so you open the can or the box, whatever it was in, and it's open to atmospheric pressure, it's going to absorb that moisture. So it's pulling hydrogen in. So at that point, the way that code regulation sees it in most shops will say, take the 7018, it's a low hydrogen rod, it's designed to be a low hydrogen rod. You need to be able to put it in a rod oven, bake it up to 250, 350 degrees, and let it sit there. And what that does is it dries the moisture out of it, okay? So that way there's no moisture within it that's going to get pulled into the weld pool and create little spots of porosity, aka hydrogen, inside of the weld pattern. And if we get enough of those lined up, it's kind of like Swiss cheese or holes in a bridge. What's going to happen is the dots are going to connect and we're going to have a weld failure, okay? It'll start cracking, and cracking is the number one failure in all welds, because it is literally, there's no more metal fusion there, okay? They're two separate pieces at that point. And that's when we have catastrophic failures. So what we're going for there is the low hydrogen helps eliminate the process of hydrogen entrapment, porosity, and so forth. Again, it's still up to you to make sure that you perform the correct welding technique in order to aid and help in no porosity and hydrogen cracking. But the rod is designed to help improve. Okay, the covering makes starting the arc easier as the beginning weld. Again, it serves as an insulator. It allows greater variation in arc length, partially because, think about it. You have the metal piece here and your base metal here, so your electrode in here. Well, as the droplets are falling, they're helping create that path to ground for electricity, okay? If we get too far away, it'll no longer be able to do it. But as we get closer, we can get a little bit more fluctuation, which sometimes we need, because we might be out of position a little bit, or just a slight fluctuation. We're not a machine, although I've seen some folks that could weld like it was a machine grade weld. It's amazing how talented some people really are, okay? But it helps create that path to ground for that electrical arc. and allows them some variation for length. It also helps pull into the center of the pool instead of spraying over. So when you're thinking of your welding rod, you have to think kind of like a pressure washer, okay? So your welding rod doesn't just come straight down in a normal pattern. It's kind of like a pressure washer if you're washing your car. It's got an angle, a weld pattern angle. So a lot of times the way I like to explain it is if you were to take your welding rod, you could think of your welding rod being like this, okay? And you can think of your spray pattern coming out of that electrode kind of that way. So as we get into angle patterns here later on in this conversation, I'm going to discuss how we want to position our electrode as well, okay? We talked about how it slows down the cooling rate. However, it also speeds up slows down the freezing rate, and it slows down the cooling rate, I mean. So this is important. This goes back to that annealing. Anytime we take 6,000 degree metal or a welding arc in the weld pool and we walk away from it, it's going to solidify. So it goes from 6,000 degrees down to at least below 2,800. We know that, right? Because that's the melting point. So that's a drastic drop. At that point, we want to slow down how fast it cools off. If we go over to the water tank and we dunk it, then it becomes very brittle. We just quenched it. And that becomes a problem because that makes, say you've got everything really, really excited, like kind of like your muscles, okay? So we just went for a run, it's a nice hot day, everything's good, we're nice and loosened up, and then all of a sudden we jump into, say, 0 degree water. What do you think is going to happen? Our muscles are going to tense up, we're going to lock up, and we're going to cramp up. Well, the grain structure within metal does the exact same thing, okay? The atoms are within this boundary and they're free to float, and the second you quench that material, those atoms and molecules they just shrink up and they freeze in position. So that's what happens is sometimes you can get a great amount of distortion, warpage, you get a really fine grain boundary, but it can also be very brittle. We'll discuss that more going through other chapters, but just start thinking in that process now. We want to let it cool down nice and slow instead of quenching it every time. Now for speed, in the first couple welding classes, just doing fillet welds, yeah, I'm going to have you go over and dunk it. That way you can keep going. But once we start into the open groove plate or any groove plate that we're going to bend, then there will be no more dunking and quenching of your weld pieces. We need to let it cool down slowly in between each weld pass. Okay, it should have a melting point lower than both the core wire and the base metal. Slag must have lower density than solidifying weld metal and able to solidify quickly when electrode used for overhead and vertical welding. When we get into out of position welds, then we're fighting gravity. And then in the next course, welding 2, you're really going to notice how bad you'll be fighting gravity. What we're doing is literally taking and pushing liquid into positions that are defying gravity, okay? So as we're dumping water, so to say, we got a garden hose, and we're dumping water on a wall coming uphill, okay? And what happens to the water is it's just all going to run down. Well, luckily for welding, it'll solidify in between. But that's one way to think about it, is to think we're trying to manipulate liquid to a pattern to where we can get the appearance and the characteristics we want out of it as well, okay? Overhead, same thing. If we just took a garden hose straight up there, it's all going to come back down. So we have to be very careful about the correct rod selection, the correct rod angle, and how our travel speed is, our body position, so that we don't end up getting burnt from those metal droplets that might be coming down as well, okay? Okay, classified according to their purposes. Okay, let's back up and catch out of the book real quick. Okay, so page 311, chapter 12, control of arc characteristics. Go down to the second paragraph. It starts out, as a rule, when welding with SMAW electrode, the max arc length is never greater than the diameter of the bare end of the electrode. That is a very important piece. Now, there's times that we can crank the amperage up and get it to maintain itself. However, that rule of thumb is very true, in my opinion, on everything. If you're running a 1/8 inch electrode, you want to be about an 1/8 inch off of your workpiece. That's kind of the golden ticket, so to say. You want to stay about that distance. If you're on 532, you can get about 5/32 of an inch off of the base metal. That's roughly where you want to stay within guidelines, okay? Back to the book. Next paragraph down, it says the covering concentrates the heat of an arc on the work and thus causes an increased melting rate. The flux contains elements that ionize at the temperature of the arc and form a conducting path between the poles during the periods when the metal arc is extinguished by the transfer of globules of metal. Kind of what we talked about earlier, path of least resistance, right? Okay, jump down to the next paragraph. Underneath composition of electrode coverings, the type of covering affects the arc length and the welding voltage, as well as the welding position in which the electrode can be used. Its composition is very important. The covering should have a melting point lower than that of both the core wire and the base metal. Okay, so I want you to jump down to the bottom of that paragraph and come up 1, 2, 3, 4, 5 sentences right in the middle. It starts out, the coating is primarily responsible. The coating is primarily responsible, so we're on page 312, top paragraph, about halfway down, right in the middle, starts out, the coating is primarily responsible for the differences between electrodes. The core wires for carbon steel electrodes are usually made of the same type of steel. However, some alloys are transferred more effectively through the core wire than through the coating. Okay, so we look here, classified according to their purpose. Next paragraph down, materials for electrode coverings. Materials used in the coverings of shielded arc electrodes may be classified according to their purpose. Okay, let's jump on down to the next one. We're going to talk a little bit about a few of them real quick. So sodium and potassium silicates are universally used as binders. Some organic gums also have a limited use for this purpose. Ferroalloys and pure metals serve as deoxidizers and alloying ingredients. The alkaline earth metals are the best arc stabilizers. Wood flour, wood pulp, refined cellulose, cotton linters, starch, sugar, and other organic materials provide a shield of reducing gases. So that's kind of interesting to think that wood pulp is within our 6010 5P electrodes. Smell it when you burn it. It kind of gives off a fire burning smell, so forth. Fluxes and slagging ingredients. So we just talked about provide shield of reducing gases. In the book, fluxes and slagging ingredients. Okay, fluxes and slagging ingredients include silica, alumina, clay, iron ore, rutile, limestone, magnesite, mica, and many other minerals, as well as some man-made materials, such as potassium titanate and titanium dioxide. Boy, some of the terminology in here, I gotta stop, sound it out. I know that there's probably a few of them I've made some errors on, but again, thank goodness we're not in chemistry class, correct? However, there's certain properties within. So for example, silica, and let's say potassium, alumina. Now these help the machinability of a material as well, okay? So By adding alloys such as silica and alumina and titanium dioxide, so forth, it helps prevent things like hot tearing of materials. So as you're machining, this is on a very, very microscopic scale. I mean, very microscopic scale. As you're machining it down, it prevents the metal from being torn away instead of cut away. So you want to make sure it's a nice smooth cut, right? So you kind of slice it in half. So let's give an example of slicing butter with a warm butter with a knife versus butter that's been in the freezer, right? So if you've got a knife that you're slicing warm butter with, it goes through nice and easy, nice, good, smooth cut. But if you're going to cut a piece of butter that's been in the freezer, you're going to have to get a sharper knife, and you're also going to take a chance of pieces of the butter coming out when you're done. It's going to be a rougher cut, so to say. And that's where alloying elements such as that, and other ones as well, not just that one, but the many different alloying elements have different purposes that they add to materials. Okay, moving on. Polarity, interchangeability. So out of this one, I'm just going to read from the slides. Okay, it's a good paragraph to read to understand the DC electrode negative versus DC electrode positive, so forth. Composition of covering determines best polarity of electrode used for DC applications. All right, does that mean you're going to have to memorize all of them? No, there's a few key ones that you will need to know. So for example, even 7018, usually there's a 7018 alternating current rod versus just a plain 7018. 6010, you know, it needs to be run on DC. 6011, 6012 can be run on direct current or alternating current, either or. Okay. A lot of times, especially starting out here, it just takes you a little bit to get used to it. There's just so much information out there that's getting thrown at you here in the first course even. So you can start familiarizing yourself with tables 12.1 through 12.5. Right here, 12.4, table 12.4 on page 313 is a very good characteristics of mild steel electrodes only. So we got 6010 on the top, about halfway, 2/3 way down, 7024, and then 7018 down below it. One thing I want you to take notice of is look at 7015, 7016, and 7018. Those three are classified as low hydrogen electrodes. So it's just important to know, if it's a low hydrogen electrode, it ends in an 8, a 5, or a 6. Okay? So that number right there tells you it's a low hydrogen electrode. It needs to be treated that way, quite possibly put in a rod oven to maintain its low hydrogen abilities or characteristics, so forth. Now as we look at tables 12.1 through 12.5, we're going to get more in depth of base metal composition, physical properties, and so forth. But it's important to start this conversation right now, even in the first course, okay? So let's talk about, table 12.1 talks about physical properties of welds, your ultimate strength, your yield point, elongation, reduction of area density, so forth, okay? Down below you'll see a comparison of core wire composition. So you can see, you know, look at carbon. So we're talking very small percentages. They're not even 1%, they're 0.1% of carbon, okay? Or 0.4% of manganese, so forth. So when we're talking percentages of alloying elements, this is a very, very small amount, but it's spread throughout the whole entire flux coating, and it's distributed at an even rate, okay? Let's look down there at table 12.3. Right here, here's the main thing I wanted you to take over. This isn't the 12.3 slide in your book, but this is a good slide to help explain a couple things. So look at the property number. It says E60XX. So whether it's 6011, 6010, 6015, whatever, 6018, what we're looking at is the first two digits. Okay, so the property number, in this book it says 62. However, it is 60. 60 to 62, you know, the general thumb is it was 62 was the original ones. However, if you read in through the AWS standards, it has to be a minimum of 60. That's the minimum tensile strength. If this were to say 60, your minimum tensile strength has to be 60. Okay? So forth with 70. Look at your minimum tensile strength is 70,000. So this is pounds per square inch. This is PSI, pounds per square inch, not 70,000 pounds. Because when we start talking about pounds, we might be thinking 70,000 pounds of force. That's totally different depending on surface area, the amount of area we're dealing with, and so forth. So it's pounds per square inch, PSI. Remember, a lot of times they'll throw some tricks in there. Maybe it'll say 70 pounds per square inch, 70 PSI. So PSI and pounds per square inch are the exact same thing, okay? A lot of our test questions and core material is going to be designated by the American Welding Society. They're the main governing body of the welding standards within the U.S. Still today. There are a lot of other agencies, however, they work together quite often, and most of the definitions, terms, and standards was produced and written by engineers for the American Welding Society, and ASME, API, and all the other organizations have kind of adopted the American Welding Society's definitions and terms. Now ISO is a little bit different. We'll discuss that at another point as well, okay? So we go back here, let's talk about the classification of electrodes. So it's got to be within 2.5 inches of the grip and the electrode, okay? So we'll see this number on our shielded metal arc welding electrodes. Let's talk about it a little bit. Here's the other agencies that I was discussing. They have, but most of them have adopted the American Welding Society standards for it. Talks about the mechanical properties, the type of covering, recommended welding position, and the type of current required. Series are four or 5-digit numbers prefixed with the letter E. Now this is for carbon steel electrodes only. Okay. As far as the 4 or 5, we get into the stainless. You're still going to have the E, but it might be a 308 or an E309, E316L, so forth. The 4 and 5 mainly is for carbon steel electrodes. We get into alloying and non-ferrous materials, then it changes. It can be a 3-digit number as well. All right, so the first one, E, that's basically just saying it's an electrode, okay? The next two are the tensile strength, represented in 1,000 pounds per square inch. It may be in 2 or 3 digits, so we've talked 7018, but right here, we're at 11018. So that means that the tensile strength of this is 110,000 pounds per square